My name is Hunter Manning, and this is Lab 4 of Physics 2211 at Georgia Tech, titled Oscillations. I will now briefly discuss what will be in this lab report. I will first introduce the lab while identifying the system and the surroundings. I will then dive into some key concepts behind this experiment. I will then analyze the motion of the object through the tracker software. Next, I will discuss the computational model used to predict the object's motion through GlowScript. Then I will discuss the results of this experiment, and finally, I will answer the assigned discussion questions. The goal of this lab is to predict the motion of an oscillating object using observations from tracker and create a computational model that replicates this motion. Further, this lab's focus was to analyze the different types of energies that are working among the system and its surroundings, including kinetic energy, gravitational potential energy, and elastic potential energy. The system is the oscillating mass, and the surroundings include the spring and the earth. However, to simplify the energy calculations, we can consider the system to be the oscillating mass, the spring, and the earth together. I will now discuss some key concepts behind this experiment. Based on the energy principle, the change in energy of the system is equal to the work done by the surroundings on the system plus Q. In this equation, delta E is the total change in total energy of the system, W is the work done by the surroundings on the system, and Q is the energy exchange between the system and its surroundings due to differences in temperature, but we will ignore this term for this experiment. Because we are considering mass, Earth, and the spring to be in the system, there is no work being done by the surroundings, and thus the total energy is conserved, meaning delta K, which is kinetic energy, plus delta UG, which is the change in gravitational potential energy, and delta US, which is the change in elastic potential energy, is equal to 0, thus indicating that energy is conserved. Tracker software. You can see in the tracker software shown below, which was used to map the motion of the oscillating mass over time. This software gave us the x and y values of the oscillating mass, which were inserted to an Excel file and then converted to a .csv file for GlowScript analysis. The motion of the object began at frame 6, so I began tracking the motion at this point. I also included a picture of the calibration in the top right of the screen. I will now discuss the computational model and some of the changes that were made to the original GlowScript starter code. Above, you can see the initial conditions of the ball. The mass of the ball was set to be 0.42 kilograms, and its initial velocity was set to be 0.000 meters per second. Its initial velocity was updated using the position and velocity update formulas, respectively. The original x and y positions were inputted from the tracker software, and the original x position was set to be minus 0.16 meters, and its initial y position was set to be minus 0.658 meters. G was inputted as the gravitational constant, which is 9.81. The spring constant was calculated as 6.82 and inputted as such. The initial length of the relaxed spring was 0.123 meters. The total energy of the system is the sum of the kinetic energy of the ball, the gravitational potential energy of the ball, and the elastic potential energy of the spring. The formulas for this were shown on the previous slide and inputted into the computational model. The net force acting on the ball is the sum of the spring force and the gravitational force. This is then accounted for in the velocity update formula to map the motion of the mass over time. Change in total energy of the system is the final energy minus the initial energy. These formulas and equations were inputted into the computational model to successfully map the position of the ball over time. Moving on to the results of this experiment. The results of the two models are shown below. The computational model did a pretty good job of predicting the motion of the oscillating mass. However, some points were slightly off. Some sources of error contributing to this may be attributed to air resistance, drag, and other external forces that were not accounted for in the computational model. So what does it mean? Is the total energies of the system conserved? To simply put it, yes. We are considering the mass, the spring, and the earth to be the system itself. Therefore, delta E will always remain 0. This is indicated by the orange line shown below, which remains at x equals 0 at all points in time. We will now move on to the second what does it mean question. In this, we will compare the x and y directions. The average oscillations in the x and y direction are similar, but they are not exactly the same, as you can see. The average oscillation in the y direction is slightly smaller than the average oscillation time in the x direction.